Alright kiddos, let's do a bit of a review today. Let's practice some electron configurations. We'll do some orbital diagrams, and we're also going to do some dot pictures as well. So let's start with the element sodium. Find sodium on the periodic table, kiddos, and here it is. It's atomic number 11. So we have 11 electrons that we're going to worry about. Let's first begin with its electron configuration. So we're going to go back to the periodic table and just remind you about a few things. Remember, this is what we call the S block of the periodic table. This is the P block, and here is the D block. We haven't worried about these too much, but down at the bottom we have the F block. Now remember, this first row would be analogous to the first energy level, this second row, the second energy level, the third row, the third, the fourth, the fifth, the sixth, and the seventh. Okay, so if we want the electron configuration for sodium, and it's 11 electrons, we need to go from 1s2, 2s2, 2p6, 3s1, and that takes us to sodium. So let's go ahead and write that down. 1s2, 2s2, 2p6, 3s1, and we're going to use the abbreviated configuration quite a bit today. So if you remember, with the abbreviated configuration, we take the noble gas before the element we're interested in. So the noble gas before the element sodium is neon. So if we were to put neon in brackets, folks, the configuration would be 1s2, 2s2, 2p6, then we would just write 3s1 after that. Sort of a shorthand or abbreviated way to write the entire configuration for sodium. Now for the orbital diagram, for the first element, I'm going to do the entire orbital diagram for you, but after that we'll just worry about those after the preceding noble gas. I'll show you what that means in just a sec. So the complete orbital diagram for sodium would be the 1s orbital, and we can see there are 2 electrons in there, right? 1s, 2. And then the 2s orbital also has 2 electrons. They're all paired so far. The 2p sublevel, remember, has 3 orbitals, kiddos. px, py, pz. It has 6 electrons in there. If you remember, they go in one at a time until the sublevel's half full, and then they begin to pair up. So we have my 1s2, 2s2, 2p6 so far, and then my 3s, there's just one s orbital with 1 electron in there. Now, of course, the valence electron is this third energy level electron. There's 1 there, so there's 1 dot in sodium's dot picture. So over here for the dot picture for sodium, I'm just going to put 1 dot there. And so now we have the electron configuration, the orbital diagram, and the dot picture for sodium. Okay, let's move on to magnesium, and we'll be able to go through these pretty quickly actually. Let's clear the page so it's not so confusing here right now. And so if we take a look at magnesium, it's atomic number 12. It looks like it's going to have a similar configurations to sodium. It will be, let's see, 12 electrons. Won't it still be neon in brackets? But instead of 3s1, magnesium will end with, this is the third energy level. Remember, folks, this is my S block here. It'd be 3s2. So 3s2. So the orbital diagram, we're just going to use the electrons after the preceding noble gas. So I'm just going to put the 3s orbital here, kiddos. And there are 2 electrons in it, and of course they are paired up. So the dot picture for magnesium would have a pair of electrons in it, just like that. Next up is aluminum. So aluminum's atomic number, folks, is 13. Going over to our periodic table, we're now going to be working with the P block way over here. And here is aluminum, folks. So after 3s2, we're going to go to 3p1. It's the first element in that P block. So we would have neon in brackets for aluminum, then 3s2, 3p1. If I were to do its orbital diagram for the electrons after the preceding noble gas, I'd have my 3s orbital with 2 electrons in it, and my 3p orbitals, there's only 1 electron there, so it would look like that. So in the dot picture, I would have a pair of electrons and 1 by itself. So I'm going to put a pair of electrons to the right of aluminum and 1 by itself on top. Okay, now why don't you take a minute and do the next, let's go 1, 2, 3, 4, 5, do the next 5 elements, then come back to the video and see how you did. Alright, welcome back. The next element is silicon. Its atomic number is 14. Let's take a look at the periodic table for silicon. It's right over there, and so instead of ending with 3p1 like aluminum did, it would end with 3p2, wouldn't it? So let's go back to our notes here. We would have neon, 3s2, 3p2, and so its orbital diagram, the 3s would have a pair in it, and the 3p sublevel would have 2 electrons, but remember, they are not paired up. According to Hund's rule, they don't start pairing up until the sublevel's half full. That means they have to start pairing up at that point. So in my dot picture, I'm going to have a pair, and these 2 guys will be in orbitals by themselves. So a pair, and then 1 here and 1 over there for silicon. Okay, phosphorus, atomic number 15. And so if you take a look at phosphorus on the periodic table, it's 1 over from silicon. So it would end with 3s2, 3p3, or 1, 2, 3 into the p block. So we would have neon, 3s2, 3p3. So my 3s orbital has a pair in it, and my 3p sublevel has 1, 2, 3 electrons. So my dot picture would have a pair and 3 by themselves. So a pair and then 1, 2, 3 by itself, and that would be your dot picture for phosphorus. Sulfur has 16 electrons. Its configuration would be neon, 3s2, 3p4. And so my orbital diagram would be 3s with a pair in it. And my 3p sublevel would have 4 electrons, 1, 2, 3, and there's my 4th. So it looks like my dot picture would have 2 pairs and 2 by themselves. So 1 pair, 2 pair, and 2 by themselves, and that's the dot picture for sulfur. Chlorine has 17 electrons, so its configuration would be neon, 3s2, 3p5. The orbital diagram, the 3s would have a pair, and the 3p sublevel would have 1, 2, 3, 4, 5 electrons in it. So my dot picture, you can see, would have 3 pairs and 1 by itself. So 1, 2, 3 pairs and 1 by itself. And then that takes us to argon. Argon has 18 electrons, so its configuration is neon, 3s2, 3p6. So the 3s, once again, has a pair in it, and then the 3p has all 6 electrons. It's completely full, isn't it? So it looks like I have 4 pairs in my dot picture for argon. So 1, 2, 3, 4. And we have what we call a noble gas configuration with argon. That noble gas configuration simply means that it has 4 pairs of electrons in its outermost level, its valence level, and that is a very stable configuration. Okay, now we've made it to potassium. So potassium, kiddos, is right here with atomic number 19. Notice it's the 4th row down. So when I write its configuration, the noble gas preceding potassium is argon, the one we just finished. So I'll put argon in brackets, then 4s1. So let's go ahead and write that down for potassium. Argon, 4s1. Now once again, that had 19 electrons. So if I'm just interested in the electrons after the preceding noble gas, I'd have my 4s in my orbital diagram, and there's 1 electron there. So potassium has 1 dot in its dot picture. Now notice that potassium's dot picture with 1 dot in it, folks. So take a look at potassium here, just 1 dot. It is just like sodium's dot picture up here with 1 dot. Now remember, if they're in the same family, folks, they have the same number of valence electrons, and sure enough, sodium and potassium are, and so you would expect them to have the same dot picture. Okay? All right, I gotta change pages here. So let's see if we can do that. We're going to go to the element calcium now, and calcium is atomic number 20. So we have 20 electrons to worry about. And remember, the noble gas before calcium is argon. So we're going to have argon in brackets. And it's going to be 4s, and it looks like it's 2 into the 4s. So calcium would end with 4s2. So the orbital diagram for the electrons that are involved after the preceding noble gas would be the 4s sublevel. There are 2 electrons in there, so its dot picture would have a pair of electrons in there. And you'll notice that calcium's dot picture with a pair is identical. Well, calcium's will have a pair, and so will magnesium's, folks. So if we look at the previous page and find magnesium, they're in the same family, and sure enough, they have the same dot picture. Now, next up is scandium. Scandium is atomic number 21. So its configuration would be argon 4s2. Now, what comes after that 4s2? Well, remember, this area right here is called the D block, and it always lags 1 behind the row number. So, if this is the 4th row, scandium would be in the last electron would be in the 3d sublevel. And it's the first electron there, so it'll be 3d1. Now the valence electrons would be those in the 4th energy level, not the 3rd. They're not always the electrons that entered last. They're the ones that are farthest away, not always the ones that entered last. So if I were to do the orbital diagram for scandium, I'd have a pair in the 4s, and my d sublevel, remember, has 5 orbitals in it, folks. 1, 2, 3, 4, 5, and this is my 3d, and there's only 1 electron there. Now once again, my dot picture only involves those in the highest energy level. So scandium would have a pair of electrons. And that's it for its dot picture. Titanium has 22 electrons. It would end with argon 4s2 3d2. So its orbital diagram, the 4s would have a pair in it, and then my d sublevel would have 2 electrons in it. 1, 2. Now once again, the dot picture only includes the valence electrons, those in the highest energy level. So titanium's dot picture once again only has 2 dots in it. Vanadium has 23 electrons. Its configuration would be argon 4s2 3d3. Notice, folks, vanadium's right here. It's 1, 2, 3 into the d sublevel. So 4s2 3d3. The orbital diagram, the 4s has a pair in it, and my d sublevel has 3 electrons in it, 1, 2, 3. So once again, the valence level is my 4th energy level. There's only 2 electrons in there, so vanadium would have 2 dots. Now the next element, chromium, folks, is a bit tricky. So be careful when you come to chromium. Let's take a look at where it is on the periodic table. It's right there, folks. It's 1, 2, 3, 4 into the 3d. Now it turns out that a sublevel is particularly stable when its sublevels are either completely full or half full. And you'll notice with chromium, it's 1, 2, 3, 4 electrons in the d sublevel. So you might want to write its electron configuration with its 24 electrons as argon 4s2 3d4. Now, it turns out that that d sublevel is really close to being half full. So what really happens with chromium is one of these s electrons is promoted to a d. So its configuration becomes 4s1 3d5. Now when we look at the orbital diagram, you'll see why that might be favored. The 4s would have 1 electron in it. Isn't that half full? And the 3d would have 5 electrons in it, which is also half full. And that presents a very stable configuration for these transition metals. So when I draw the dot picture for chromium, notice there's only 1 dot in it. So that's sort of strange. That happens with chromium. That would also happen with molybdenum and tungsten. Okay. All right, then we get to manganese. And so manganese we're not going to have much of a problem with. That's going to be argon, 4s2, 3d5. And so its orbital diagram, the 4s would have a pair in it. And the 3d would have 1, 2, 3, 4, 5. That's fairly stable because my 4s is full and my 3d is half full. The dot picture, the highest energy level is the 4th, would have a pair of electrons in it. Okay, and that was for an element with 25 electrons. All right, you can continue on with this and go all the way through krypton if you would, and then come back to the video, and we're actually going to do the rest of the video pretty quickly. So see how you do, and then come back and see how I did it. See you in a sec. All right, iron has 26 electrons. Did you go argon? 4s2, 3d6. So the highest energy level there is the 4th energy level, and it is a pair, so it has 2 dots in its dot picture. Cobalt has 27 electrons, so its configuration would be argon, 4s2, 3d7. Once again, the highest energy level is the 4th, with a pair of electrons in there, so it would have 2 dots. Nickel, it has 28 electrons. It's argon, 4s2, 3d8. Once again, the 4th energy level is the highest with 2 electrons, so it has a pair. Now, copper is interesting, folks. Copper is atomic number 29. You're going to want to write argon, 4s2, 3d. Let's count it over for copper now. Copper is right here, folks. 1, 2, 3, 4, 5, 6, 7, 8, 9. Isn't that painfully close to being full? So you'd want to write 3d9. Remember, those transition metals, they're particularly stable when their sublevel, their d sublevel is full or half full. So what happens with copper is one of these s electrons is promoted to a d again. And so it ends with 4s1, 3d10. So we end up with an orbital diagram 4s1, and my d sublevel, kiddos, has 10 electrons in it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it just has 1 dot in its dot picture. So that happens for copper. It'll also happen for silver and for gold. Sort of an exception to what we've been talking about. Okay, zinc has 30 electrons. That's argon, 4s2, 3d10. So once again, my 4th energy level has a pair, so zinc has a pair of electrons in its dot picture. Now that takes us to the element gallium. Now this is getting a bit confusing, so let's clear the page again so we can see things a bit better. And here's gallium, folks. So 1, 2, 3, 4 energy levels down. This is the S, this is the P, this is the D. Looks like gallium would be 4s2, 3d10, 4p1. Okay, and that would be after the noble gas argon. So we'd have argon, 4s2, 3d10, 4p1. So its orbital diagram, folks, would be the 4s with 2 electrons in it, the 3d with 10 electrons in it, and then the 4p, remember the 4p has 3 orbitals, has 1 electron in it. Now the valence electrons would be the 4s and this 4p. So it would have a pair and 1 by itself. Now that should not surprise you, because gallium is right here. It would have the same dot picture as aluminum and boron did in our earlier notes. Okay. Next element that had 31 electrons, didn't write that in there. Germanium, 32 electrons. That's going to be argon, 4s2, 3d10, 4p2. So my valence electrons would be the 4s's and these 4p's. So my 4s has a pair in it. The 3d has 10 electrons in it. And my 4p, kiddos, has 2 electrons in it. So notice in my valence level, the fourth, it has a pair, so 2 dots, and these 2 guys are by themselves. Okay? Alright, arsenic ends with argon, 4s2, 3d10, 4p3, so my valence is 4s2, 4p3. So with 33 electrons I would have a pair in my 4s, and these 3 in my p would be by themselves. Selenium with 34 electrons is argon, 4s2, 3d10, 4p4. So let me just do the valence electrons here for the orbital diagram. The 4s has a pair, and my 4p has 1, 2, 3, 4 electrons in it, doesn't it? A pair and 4 electrons. So my dot picture will have a pair, another pair, and then 2 by themselves. So a pair, another pair, and 2 by themselves. Bromine, atomic number 35. So its configuration is argon, 4s2, 3d10, 4p5. So for my orbital diagram, the 4s has a pair, the 4p has 1, 2, 3, 4, 5. So it looks like my dot picture of a pair, 2 more pairs, and 1 by itself. A pair, 2 more pairs, and 1 by itself. And then krypton, atomic number 36, is argon, 4s2, 3d10, 4p6. You can see I'll have a pair in my valence and 3 more pairs. So 4 pairs altogether around krypton. Okay? Alright, hopefully kiddos you're proficient at writing electron configurations now, doing orbital diagrams, and dot pictures. Hopefully you're really good at those. It's nice talking to you. See you soon. Bye-bye.